Hi, in this video we are going to first define a certain function or signal, and then we are going to calculate the Fourier series coefficients of the periodic extension of that signal. Now let us define the signal P of t as follows. P of t is equal to capital A t for t between minus t cap over 2 to t cap over 2 and 0 otherwise. Okay. Now if we plot the graph of P of t, we have a variation of the signal from minus t cap over 2 to t cap over 2 as follows. In fact, it traces this curve from minus t cap over 2 to plus t cap over 2, and at these points, if we look at the definition of P of t, at t cap over 2, it will be a t cap over 2, and similarly at minus t cap over 2, we will have minus a t cap over 2. Okay, now let us define a periodic extension of this P of t as follows. Define x of t as m from minus infinity to plus infinity, P of t minus m t0. We are going to assume that t0 is greater than t cap, or maybe we can also allow equality. t0 is greater than or equal to t cap. So we have the periodic extension of P of t as P of t repeated with a period capital T0. Now for T0 equal to t cap, we get the so-called Sawtooth signal. X of t becomes the Sawtooth function or signal. Now if we plot this case, we see that x of t will, the graph of x of t will very much look like the Sawtooth. So it will be the following signal. Etc. So we have the periodic repetition of this. Now you see that this point here is t0 over 2, and this point here is minus t0 over 2. So t cap equal to t0 gives us the Sawtooth signal. But let us calculate the Fourier series of x of t, not for just this case, but in general, for a certain t0 satisfying the inequality t0 greater than or equal to t cap. Now, x of t is a periodic signal. X of t is periodic with fundamental period equal to t0. So x of t will, or it can be represented as a Fourier series as follows. The superposition of the complex exponential signals e to jk omega 0 t, where omega 0 is related to t0 by means of this equality. Now, ak, the coefficients ak's can be determined by using the following expression, as we remember, 1 over t0, the integral over a period of x of t e to minus jk omega 0 t integrated with respect to t. So the most convenient interval for integration is, for our general case, from minus t0 over 2 to t0 over 2. So we have 1 over t0 from minus t0 over 2 to t0 over 2, x of t e to minus j k omega 0 t integrated with respect to t. Now, x of t is only non-zero in the interval from minus t cap over 2 to t cap over 2, and there it is equal to at. It's given by the expression at. Therefore, we have 1 over t0 from minus t cap over 2 to t cap over 2, at e to minus jk omega 0 t integrated with respect to t. Okay, so let us now look at the details of the calculation of this integral. Okay, ak was equal to, okay, we can take the constant a outside the integral. We have a over t0 from minus t cap over 2 to t cap over 2, the integral of t times e to minus jk omega 0 t integrated with respect to t. Now, in order to calculate this integral, as you see, we have t times the complex exponential function integrated. So we can use integration by parts. So let us write down the expression for integration by parts. The integral of u dv for functions u and v is equal to uv minus the integral of v du. Okay, for definite integrals, of course, this uv term must be evaluated at the integration limits. So if we want to use integration by parts, our u is, the function u is this t, and this term here is dv. So we have a over t0 then we have t, and v is e to minus jk omega 0 t divided by minus jk omega 0. So this expression must be evaluated at the integration limits, minus t cap over 2 and t cap over 2. Then we have minus the integral okay, we have also, of course, the multiplier a over t0, the integral of v du. So we have e to minus jk omega 0 t, and u is t, therefore du is dt. Okay, we have v du, sorry, this is, v is e to minus jk omega 0 t divided by minus jk omega 0. Okay, so let us look at the first term. We have a t cap over 2t0, because we substitute t equal to t cap over 2, and we have e to minus jk omega 0 t cap over 2. Then we have, okay, when we substitute minus t cap over 2, we are going to have e to jk omega 0 t cap over 2 divided by minus jk omega 0 minus jk omega 0. So let us look at this expression once more. When we substitute t cap over 2, we get okay, e to minus jk omega 0 t cap over 2, and we have t cap over 2 as the multiplier. Then we have minus t cap over 2 divided by minus jk omega 0. Okay, then that is correct. Minus, okay, let us look at the second term. Now, this integral is from minus t cap over 2 to t cap over 2. So we have we can take the constant term j k omega 0 with a minus sign outside the integral. So we have a over t0 j k omega 0, and we have e to minus j k omega 0 t divided by minus j k omega 0 evaluated at the integration limits, minus t cap over 2 up to t cap over 2. Okay. Now, we have nothing to do with this first term. It is the last expression, the final expression we obtain for that term. But if we now consider this term here, we have a over t0 jk omega 0 e to minus jk omega 0 t cap over 2 minus e to j cap omega 0 t cap over 2 divided by minus jk omega 0. Now, similar to what we have done in the Fourier series coefficient calculation of the rectangular pulse, we can substitute for omega 0, instead of omega 0, we can substitute 2 pi over t0. So we are going to have the following expression: a over t0 jk omega 0. Okay, now this expression here is minus 2j sine k. Instead of omega 0, we substitute 2 pi over t0 t cap over 2 divided by minus jk omega 0. So these j terms will cancel out. Okay, and also here we can do the following. We can multiply and divide by t cap. Just multiply this by expression by t cap and divide it by t cap. So I'm going to just transfer this t cap to this expression over there. A t cap divided by t0 sine k pi t cap over t0. Okay, here instead of omega 0, of course, we are going to substitute 2 pi over t0. So we will have k pi t cap over t0. T cap coming from this expression over there. So now we recognize this expression here as a sinc function. And also, I have just forgotten to write that down. We have 1 over jk omega 0. Okay, one final remark related to this expression here is that now a t cap divided by t0 multiplied by this sinc function, sinc of pi t cap divided by t0 is the Fourier series coefficient of the rectangular pulse signal. That Fourier series coefficient is multiplied by 1 over jk omega 0. Now, in a later video, we are going to see the meaning of this operation here. Now, also let us look at the first expression. We have two complex exponential terms. Now let me see whether we have the sign correct. In fact, we have, when we substitute minus t cap over 2, we have a minus sign as well. Therefore, this plus minus sign must be corrected as a plus sign. Okay, we are going to see the meaning of this expression as well in a future video. Thanks for watching.